Hi everyone, welcome to the video on sequences and series for Math 1452 at Texas Tech University, which is Calculus 2. So in this video, we're going to be breaking down what is a sequence, what is a series, and what do we do with them. So first off, we can think of a sequence just as a function. So our normal function notation that we have is f of x. But what we're going to use for our sequences is actually the notation a of n. So the reason that we have this change in notation is that the inputs of our function are only the positive integers, which are also called the natural numbers. So that's why we use the letter n to denote the natural numbers or the inputs of our function. And so if we look at the example here, a of n equals 1 over n, we can look at the different outputs of this function given the inputs 1, 2, 3, 4, and so on. So if our input is 1, then 1 over 1 is just equal to 1. If our input is 2, then 1 over 2 is 1/2, 1 over 3 is 1/3, 1 over 4 is 1/4, and then 1/5, 1/6, and so on. So you can see that these inputs have an ordering to them because we only input the positive integers, we start at 1 and increase. So whenever we're looking at these sequences, oftentimes instead of including the parentheses, we're just going to make that in a subscript and have this a sub n, and that's going to be called our general term. And the other terms in the sequence are just going to be a sub 1, a sub 2, a sub 3, and those are specific terms where we plug in n equals 1, 2, 3, and so on. So oftentimes our sequence, we're going to write it in this notation that has these curly braces. And so that general term an is inside. And then on the right-hand side of the curly braces, we have n equals 1 as a subscript and infinity as a superscript. And what this reminds us is that our inputs are starting at 1 and then increasing till infinity. So our inputs are 1, 2, 3, 4, and so on. And we will often just look at these sequences by listing out our outputs. So listing out A1, A2, A3, where we evaluate this function on 1, 2, 3, and so on. So for this example, 1 over n, whenever we list out our outputs, we are listing out 1, 1/2, 1/3, 1/4, 1/5, and so on. And we write this as many times as we want. And then we know that it's going to continue. So we add the ... to show that's going to continue to infinity. So in this way, we represent a sequence as a list of outputs of a function, starting when we input 1 and increasing 1 integer at a time. So sequences are often talked about in relation to series, where a series is a mathematical summation and it's denoted like so. So you can see just comparing what's highlighted there in yellow that a summation has a general term an, has a general term an, that's a placeholder for some algebraic expression. And we, instead of listing out what our outputs are, we are instead going to add them all together. So this sigma summation symbol you may have seen, it is an uppercase Greek sigma. So you may remember this sign from Calculus 1. We use this summation symbol to help us define an integral whenever we were finding area under a curve. So that's an uppercase Greek sigma, and what that tells us to do is to add. So that's why we take the terms and we add them together. So again, let's look at the example of where our general term is 1 over n, and look at the series, the sum from 1 to infinity of 1 over n. So all that's going to be different here is that instead of listing out our terms, we're going to add them together. So we have 1, when we plug in n equals 1, our term is 1. When we plug in n equals 2, our term is 1/2. When we plug in n equals 3, our term is 1/3. When we plug in n equals 4, our term is 1/4, and then 1/5, 1/6, 1/7, 1/8, 1/9, and so on. And then again, we can put the dot, dot, dot to show there are more things that we're adding up here, but we're just not going to list them all. So this is kind of the fundamental difference between a sequence and a series. A sequence is a list, and this tends to be how we use this in everyday language. And a series is something that's added together. You can think of this as the World Series in baseball, how you add up the wins over that series to figure out who the overall winner is. So what do we do with these sequences and series in math? So our main objective is determining their convergence. So sequence convergence has to do with what that general term is going to look like in the end, but series convergence has to do with, well, we're adding up some numbers. There's going to be an answer there once we add up those numbers. So we say that a series is going to converge when we take the limit at infinity of that general term. And when this limit exists and is finite, then we're going to say that that sequence converges. So all this kind of means is these terms are not increasing until we get to infinity. There's some boundedness happening where these numbers may be decreasing, they may be increasing, but whatever's happening, they're not going to get so large or so small that they're positive or negative infinity. Series convergence, on the other hand, has to do with, well, when we add up all of these numbers, when do we get something finite? So whenever we actually add up all these numbers, is that summation less than infinity? So one way that we're going to look at determining series convergence is actually looking at what's called the partial sums. So what we're going to have is we're going to have SK is going to be that same summation starting at n equals 1. However, instead of going all the way up to infinity, we're just going to go part of the way. And so we're going to go all the way up to k. And so this is going to be a1 plus a2 all the way up to ak. But we're going to stop there. And we're going to see, okay, is there some way that I can simplify this summation? So in the case of fractions, can I find a common denominator and actually add things up such that when I evaluate this limit as k goes to infinity of sk, does that exist? And is that finite? So for sequence convergence, we end up evaluating this limit at infinity. And for series convergence, we also end up evaluating this limit at infinity, but series has this added step of actually finding what that sk was. So remember that this sk is going to be talked about as the kth partial sum. Because we're not adding up everything, we're only going part of the way and stopping at k. So again, you may remember from Calculus 1 when we evaluated these limits at infinity, and we're going to use some of those same tools here. So specifically, when we learned this in Calculus 1, we learned some tricks of comparing the degree in the numerator and the degree of the denominator whenever we had irrational functions or whenever we divided polynomials. So for example, if we took the limit as x goes to infinity of, let's say, x plus 1 over x squared, we learned a trick that we could just compare the degree of the numerator and the degree of the denominator. So here, the highest power of x in our numerator is 1, so the degree is 1. And in our denominator, the degree is 2. And because that degree was bigger on bottom, we can conclude that this limit is 0. So again, this should be something that you saw in Calculus 1. And what it had to do with was if our power on the bottom was bigger, then we knew that that limit was 0. And we can extend this same concept to not just looking at polynomials that have a specific degree or highest exponent, but looking at other functions as well. So we're going to create what we call a tower of power. and it compares essentially the slopes of different functions. So the smallest thing on our tower of power is going to be the natural log function. The next is going to be the square root. Next is just going to be the identity function. Next is going to be raising something to a power p. Next is going to be whenever we have some number or some constant raised to a power. And next we're going to have the factorial. And lastly, we're going to have when we have n raised to the n. So again, this is comparing growth of a function. And when you think growth, you can think, well, how fast is it changing? And when you hear that, how fast is it changing, you should immediately think, oh, well, that's rate of change. And all that tells me is a derivative. And a derivative is just a slope. So whenever you kind of think about what these functions look like graphically, so what does the ln of x look like? Well, it looks something like that. The square root looks something like this. The identity function looks like this. A power looks like that. A number raised to a power, we can think of the exponential, which looks like so. And you can see that as we go along, those slopes of those functions are increasing. So whenever you kind of doubt or have trouble remembering, okay, well, which of these has faster growth, you can just picture those graphs of these parent functions and see, oh, okay, this is what the slope looks like. So these last two, this n factorial and n to the n, are things that we haven't really looked at in math classes before. So you may not be as familiar with their graphs to kind of compare. But just remember that they are the biggest two functions we're going to look at, and that n to the n is the biggest. So with the tower of power, if we have some general terms an, we can compare, does the denominator grow faster than the numerator? And in that case, that limit is going to be 0. Just like whenever we looked over here at this limit, if the degree on the bottom was bigger, well, then that limit was 0. The same thing is going to happen here. If our denominator has faster growth, then that limit is going to be 0. So let's look at these 4 examples. So I'm just going to say, in my first example, my numerator was here, and my denominator was here. Well, since my denominator is further up on the tower of power, that limit is 0. For the next one, we have the limit n over e to the n, and my numerator is here, and my denominator is here because c is just some constant. And again, because my denominator is higher, that limit is 0. Next, we have ln of n over n to some power. So our numerator is here, and our denominator is here. And again, since our denominator is bigger, that limit is 0. And finally, we have n factorial over n to the n. Our numerator's here, our denominator's here, and that limit is 0. So these are limits that you may not have been able to evaluate before, but all it comes back to is evaluating, well, how fast is my numerator growing in relation to my denominator, just like comparing degrees like we did in Calculus 1. So that's going to be it for this video, just talking about the basics of sequences and series, and then a new limit strategy we're going to have. In the next video on this, we're going to be looking at more specific examples of sequences and series and determining their convergence.